In this video, we're going to look at completing the square as a algebraic technique that we can use for integration. And before we get into completing the square, we're going to start off by just reviewing a couple integration rules, and then I'm going to give you a couple new rules to consider. So these two rules we should be familiar with from our derivative rules that we learned previously, and we're just flipping those derivative rules and turning them into antiderivative rules or integral rules. Integral of 1 over x squared plus 1 is going to be inverse tangent of x plus c, and then integral of 1 over square root of 1 minus x squared is going to be the inverse sine of x plus c. But what if these numbers were not 1? What if we had different numbers in that place of the constant? 1 over x squared plus a squared. The rule is this is going to be equal to 1 over a inverse tangent of x over a plus c. Now, hopefully you're wondering, well, why is that the rule? And stay tuned. In this video, I'm going to show you. And then similarly, if we had 1 over square root of a squared minus x squared, this is going to be inverse sine of x over a plus c. And hopefully at this point you're wondering, well, why is there not a 1 over a in front of the inverse sine like there is for the inverse tangent? Those are questions we should be asking, and hopefully I'm going to answer those for you before we finish this video. So I'm going to start with a really simple example. And this example does not involve completing the square, just showing how to apply one of these rules. And hopefully you can see, because of the square root, that we're going to be using the inverse sine rule. So if this is a squared minus x squared, as is shown here, then my a would have to be equal to 2. And so this is going to be equal to inverse sine of x over 2 plus c. So that's how we would use the rule for a simple version of this type of problem. But let's look at another example that involves completing the square. So here we have the integral of 1 over x squared plus 4x plus 8. Now, when we want to try completing the square as a technique for integration, we need an even-powered exponent in the denominator because it has to be even-powered in order for us to complete the square. Most of the time it'll be an x squared, but this technique would work if this was an x to the 4th or an x to the 6th as well. But most of the time what we'll see is an x squared, and then just a constant in the numerator. So to complete the square, what we're going to do is just look at these first two terms, and what we want to do is add on a constant to these two terms that will cause it to be the square of a binomial. And so let's review what that looks like. If I have a binomial squared, a plus b squared, of course that's equal to a squared plus 2ab plus b squared. So what I want to do is x squared plus 4x, that's going to be my a squared plus 2ab. I want to figure out what b squared can go in here to complete this square, to turn it into a binomial squared. So what I'm going to do is I'm going to rewrite this x squared plus 4x. We're going to add in some number in this square to be the b squared. But if I add in something extra here, I have to subtract it as well to keep the expression equivalent. And then my plus 8, I'm just going to put that out here on the end. So now let's think about this. This is going to be a squared plus 2ab plus b squared. So if x squared is a squared, obviously my a is equal to x. And that means if a is x, then in this part, 2b has to be equal to 4. And if I solve for b, 4 divided by 2 is 2. My b equals 2. And so b squared has to be equal to 4. So I'm going to add in 4 here, and I'm also going to subtract 4 to keep it equivalent. So now this part of my expression here, x squared plus 4x plus 4, that's equivalent to, or it's in the form of a squared plus 2ab plus b squared. My a is x, and my b is 2. So now I can rewrite my integral as this part becomes x plus 2 squared. And then my constants that I have left out here, -4 and +8, that becomes +4. So now we've rewritten the integral. And now it is in a form that we can integrate just using our rule that I gave you previously. I don't just have x squared though, but I do have an a squared here. My a is going to be 2. We need to think about this kind of like u substitution. My x plus 2 is a u, it's a something, but the derivative of that is just 1. And when my derivative is 1, I don't have to do any special substitution or anything because the du and the dx are going to be equal to each other anyway. I can just think about this as something squared plus 4. And so if I use my rule up here, this is going to be equal to 1 over 2 inverse tangent of, in this case, not just x, but my something, which is x plus 2 over 2 plus c. Now, hopefully you're wondering still, why is that the rule? So I'm going to work this problem. I'm going to go back to this step right here, and I'm going to show a few more steps just to show why this is the rule. If you're okay with just knowing the rule, you can fast forward the video just a bit. Okay, so this new rule that I gave you today, it is certainly based on this rule that we're familiar with as a derivative rule and now as an antiderivative rule. It all goes back to this. One important feature of this rule is that we need to have a plus 1 here in this part. We need to have something squared plus 1. And what I'm looking at over here is a plus 4. And so what I'm going to do is factor that 4 out of the denominator and bring it out to the front of the integral. And so when I do that, when I factor out a 4, the 4 divided by 4, that's going to become 1, which is what we need it to be. This becomes x plus 2 squared over 4, because I have to divide both of these terms by 4 when I factor it out. Now, another thing, so now I have the 1 that I'm looking for, but I also need the other part of my denominator here to just be something squared. And I don't quite have that in this version. So instead of this being x plus 2 squared over 4, I'm going to change this to x plus 2 over 2 and square the whole thing. Plus 1 dx. Now I have it in the form of something squared plus 1, which matches my rule up here. But we do need to use u substitution here, because if I take a derivative of this something, it's not just 1. And so we've got to think about what special kind of substitution do I need to make this work. So my u is going to be x plus 2 over 2, or if you want to think about it like this, x over 2 plus 2 over 2, might help you see a little bit better that the derivative, my du, is going to be 1/2 dx. And that means that dx is going to be equal to 2 times du if I multiply that 2 over to solve for dx. So now I'm going to rewrite the integral doing the u sub. So 1/4 outside. This becomes 1 over u squared plus 1. And then in the place of dx, I'm going to put times 2 du. And now I have it in this form where we can use our antiderivative rule. The 2 and the 4, put those constants together. The integral of 1 over u squared plus 1 is going to be inverse tangent of u plus c. And then I'll reduce the fraction and plug back in that u is x plus 2 over 2 plus c. And at this point, you can compare to the answer we got before, and you can see that we got the same thing. Let's look at another example. So in this example, we've got the integral of 1 over the square root of 3 minus x squared minus 2x dx. Again, what we're looking for here is the square root of the x squared something that looks similar to our inverse sign antiderivative rule, which we should be familiar with. The x squared needs to be negative, and that is certainly the case here. And so this is a candidate for completing the square to see if we can get this in a form that we can integrate. Now, when I complete the square, I really prefer for that x squared term to be positive and to be the first term. And so the first thing I'm going to do here is factor out a negative sign. Not out of the square root. I'm keeping it inside the square root. I'm just going to factor it out to the front and rewrite this stuff in parentheses. If I factor that out, my x squared is going to become positive. This minus 2x will also become positive. I'm skipping some space because I'm going to complete the square here, but I want to finish with this factoring out of the negative. My 3 was positive, so it's going to be a minus 3. Now, these are the two terms that I want to complete the square with. So I'm going to add in something, and then I also need to subtract out that same thing. So I'm going to put in the plus square minus square that I need for my completing the square. And then dx, of course. Okay, so we're ready to complete the square. This is going to be a squared plus 2ab plus b squared. Obviously, a is equal to x. That means that if the a is x, then 2b has to be equal to 2. And b is 1, and so my b squared is equal to 1. So I'm going to add in 1, and I'm going to subtract 1 to keep it equivalent. And so now we're ready to rewrite the integral. This x squared plus 2x plus 1, my a is x, my b is 1, so that is equivalent to x plus 1 squared. I need to put another parentheses here. So that takes care of those three terms, and then I have negative 1 and negative 3, which is minus 4 dx. Okay, so now we're kind of close to the form that we're looking for, but remember, I want the something squared to be negative, and I need the constant in the front to be positive. I need it to be in that 1 minus x squared form. And so, or the a squared minus x squared form. So I'm going to multiply the negative back inside. Switch the order of my integral here, of the expression in the denominator, not the whole integral. But if I multiply the negative back in there, my 4 becomes positive, and this x plus 1 squared becomes negative. Now that we have it here, we can use the new rule that I gave you, which looks like this. And so I don't exactly have x squared, but I have something squared. And that something, if I think about it like a u, my du would be 1. So I don't have to do any kind of special substitution. I can just think about it as a something, think about this as a something, and use the rule. This is going to be equal to inverse sine of my x, or my something, which is x plus 1, over a. If my 4 is the a squared, then my a has to be 2 plus c. And that would be our answer. Now, again, hopefully you are wondering, why does it come out that way? Why do I not have the 1 over 2 in front like we did previously with the inverse tangent? I'm going to show you why that is. If you're good with the rule, you can stop the video now and move on to practice. All right, so to see why the rule is the way that it is, I'm going to go back to this point in the process when I had completed the square and multiplied back in the negative sign to get this in this form. Now, this rule is based on the basic antiderivative rule that the integral of 1 over the square root of 1 minus x squared is the inverse sine of x plus c. And so again, just like with inverse tangent, I need that constant to be a 1, and my problem here is that I have a 4. So I'm going to do the same thing. I'm going to divide everything in the denominator by 4 and factor that out. But remember, this is under the square root. So basically, I'm factoring out a square root of 4. If I divide the, let me put my square root here. If I divide the 4 by 4, that's just going to become 1. And then I need to divide the x plus 1 squared also by 4 dx. Now again, I have x plus 1 squared divided by something. I really need that whole term to be just something squared. And so I'm going to rewrite that. Let's go ahead and make square root of 4 2. Integral 1 over the square root of 1 minus. So this is going to become x plus 1 over 2 squared. When I make it squaring the whole thing, that 4 needs to become a 2 dx. And so now we're in a form, I've got that 1 there, but I have this expression in the x or the something spot. So I'm going to do u substitution. U is equal to x plus 1 over 2. Du is going to be 1/2 dx, just like we saw in the previous example with inverse tangent. And if I multiply that 2 over, dx is equal to 2 times du. So I'm going to rewrite the integral. 1/2 1 over the square root of 1 minus u squared. And then in place of dx, I'm going to put times 2 du. And now you can see why we don't have that 1/2 in the front, because in this case, the 2 actually cancels out the 2. With our inverse tangent previously, we had the 2 in here, but we had 4 outside because it wasn't square rooted here. When we factored out the 4, we didn't have the square root on it. Here, I factored out the square root of 4, and it became a 2. Those are going to divide out, and so this is equal to inverse sine of u plus c. And if I plug back in what u is equal to, x plus 1 over 2 plus c. And now we have the same answer that we got using the rule that I showed you.